Hi everyone, this is Lesson Time Dilation. So before we start with today's lessons, concepts, questions, so let me ask you something interesting. Have you ever watched a movie where someone travels through space, comes back and realizes that the other people have aged much more than they have? Right? This sounds like science fiction, but it is very much connected to real physics. Like, for example, in one of the movies that is very close to me and is one of my favorite movies, like Interstellar. So the astronauts visit Miller's planet. For them, only a short time passes, but when they return to the main spacecraft, Romilly has aged by about 23 years while waiting for them. So in that movie, the time difference is mainly because of very strong gravity near a massive black hole. So it is not exactly the same type of time dilation that we are going to calculate today, but the big idea is very similar. Different observers can measure very different amounts of time. Another example is Lightyear. So in that Lightyear movie, Buzz goes on very fast test flights. For Buzz, each flight feels very short, but when he returns, years have passed for the people who stayed behind. His friend Alicia grows older, while Buzz has aged much less. So today's lesson is about this strange but very real idea. Time does not always pass at the same rate for everyone. So in this lesson, we are focusing on speed-based time dilation. So we are asking what happens to time when something moves extremely fast, close to the speed of light. So this is what we are going to work on today. So the big idea is time can pass differently for different observers. And today in this lesson, we are going to discuss speed-based time dilation. But in the movie that I had discussed, Interstellar, it was basically gravity based, right? This is both the main idea is same, it's different in terms of speed and gravity. So here is what we are going to do in today's lesson. First, we will understand what time dilation means in simple words. Second, we will learn the difference between proper time and the dilated time. Third, we will learn how to use the time dilation formula. Then we are going to solve two examples. The first example is a spaceship and twin question, which is very famous physics question. The second example is a muon lifetime question. So the spaceship example feels like science fiction, but the muon example shows that time dilation is not just a movie idea, it is something we actually observe in physics. So by the end, you should be able to look at any time dilation question and ask who is moving, which clock travels with the object, and who is observing the motion. So let's first discuss about the concept before we start with this question of twin and spaceship. So let's first discuss the concept that we should know. So first concept that we should know is time dilation. So what is time dilation? I'll start with a very simple idea. So let's say in everyday life, we normally think time is same for everyone. So if I say I studied for 30 minutes, you could assume that 30 minutes passed for me, for you, and for everyone else sitting around. So that works in everyday life because we are moving at normal speeds. But Einstein showed that when something moves extremely fast and especially close to speed of the light, time is not measured the same way by everyone. So this effect is called time dilation. Now, why do we not experience this time dilation in day-to-day life? Because we do not know anything that moves so fast as close to speed of light, right? In normal day-to-day life, we are not familiar with that kind of speed. So here is the most important sentence for this. A moving clock is observed to run slower. So whenever there is a moving clock, it would be observed to run slower. So the person moving does not feel anything strange. If you are inside the spaceship, your watch looks normal to you, your heartbeat feels normal, everything around you feels normal. But an observer on the earth watching that spaceship move very fast measures the spaceship clock running slower. So from Earth's point of view, less time passes on moving spaceship. Right? So if a moving clock runs slower, would the astronaut age more or less compared with the person on Earth? Think about it. So, yeah, of course, the astronaut would age less because less time passes on the moving spaceship clock, right? So, what is the important thing to remember whenever we are dealing with time dilation? Moving clock means observed to run slower. So always remember moving clock, observed to run slower. And of course, moving clock should be with the speed of similar to the speed of light. So, and it leads to a very important conclusion that time is not absolute. So different observers can measure different times. So time is not absolute, which is the very important implication of time dilation. Time is not absolute. So time is not absolute. Moving clock runs slower and the speed should be close to c. C is the speed of light. Now we need to learn a very important term, proper time. So proper time is written as delta T naught. So proper time means the time measured by the clock that travels with the object. So whenever you see a time dilation question, do not start with the formula right away. First ask which clock is traveling with the object. So that clock measures proper time. So in the spaceship question, the clock inside the spaceship travels with the astronaut. So spaceship clock measures the proper time. So in the muon question that we are going to discuss later, the muon's own lifetime is measured in muon's rest frame. So that lifetime is proper time. So here is the useful rule that you can learn, that proper time is always the shortest time interval. So proper time is always the shortest time interval. The important keywords that you should remember is traveling clock, object's own frame, and the shortest time. So if the question says 8 years on spaceship clock, what type of time is that? So it is, of course, the proper time because, again, that clock travels with the astronaut. If the question says proper lifetime of muon, what type of time is that? Again, it's the proper time. So you can think about proper time, delta T naught, time measured by the clock traveling with the object, and the proper time is the shortest time. Now let's talk about the dilated time. Dilated time is written as delta T. So dilated time is measured by the observer who sees the object moving. So in the first question that we will discuss, Earth sees the spaceship moving. So Earth measures the dilated time. In our second question, the muon question, Earth sees the muon moving. So again, Earth measures the dilated time. So dilated time is measured by the observer who sees the object moving. In both the questions, Earth measures the dilated time. So dilated time, as the word implies, dilated. So of course it's going to be longer than the proper time. So delta T is greater than delta T naught. So who measures the longer time? The traveling clock or the observer watching the motion? Of course, observer watching the motion measures the dilated time or the longer time. So dilated time is written by delta T. So it is the time measured by observer watching the moving object. So this is time measured by the observer watching the moving object. And what are the keywords that we should know? Observer watching motion, Earth observer, because we are going to observe the motion, both the questions from the Earth. So it's going to be the dilated time, and dilated time is always longer than the proper time. Now let's have this memory trick. So here is the easiest way I would tell you to remember everything. The traveling clock gives proper time. The observer watching the motion gives dilated time. So before you start solving any question, ask who is moving, which clock travels with that moving object. That clock gives delta T naught or the proper time. Then ask who is watching the motion. That observer measures delta T, dilation time, dilated time. So this step is very important because of the most common mistake in these questions is mixing up delta t and delta t naught. So you can remember this memory trick. Traveling clock would be measuring delta t naught, which is proper time, and observer clock would be measuring dilated time. So delta t naught is proper time, delta t is dilated time, right? So this is dilated, this is proper, and dilated time is always greater than proper time. So again, a quick flow chart. Who is moving? Which clock travels with that object? That clock measures proper time, delta t naught. Observer watching the motion measures dilated time, delta t. Now let's write the relation between dilated time and the proper time. So the time dilation equation is delta t equals delta t naught over 1 minus v square by c square, where delta t is the dilated time, delta t naught is the proper time, v is the speed of the object which is moving. In most of the cases, it would be spacecraft, and c is the speed of light, which is the known value. Speed of light. So this is how dilated time and proper time are related to each other. So we will see, like in many questions like this, the speed is already given as the fraction of speed of light, like 0.6 c, 0.95 c, or 90% of c, or 60% of speed of light. Like this is how speed of the moving object is given to us. This is done to make our calculation easier, because once it is in the fraction form, c and c can be cancelled, and it will make our calculation work more easy. So now let's solve the question. So the question is, you are traveling in a spaceship at 60% the speed of light. So as I've told you that it is given in the percentage form or the fraction form. So you are traveling in spaceship at 60% the speed of light. Your twin stays on Earth after 8 years on your spaceship's clock. Will your twin be older, younger, or the same age as you? And in part B, we have to tell the reason. Why? Give reason using calculations. Right. So before calculating anything else, let's understand the situation. First, we have to answer who is moving. So of course, in this, the spaceship is moving. So as you can see, what is moving here? So we can write spaceship is moving. This is the spaceship that is moving object. Another question that we should ask is, which clock travels with the spaceship? So, of course, the spaceship clock is traveling with the spaceship. So, when the question says 8 years on your spaceship's clock, that is the proper time. So, as we had discussed earlier, moving object will represent the proper time. So, 8 years means proper time is given to us. So, we can write this 8 years would be the proper time. And how do we denote proper time? It's delta T naught. Next question is, who is observing the spaceship? So the twin on the Earth is observing the spaceship, and as we had discussed earlier, Earth measures the dilated time, so delta T, right? Now, before we calculate, should Earth measure a time that is bigger or smaller than 8 years? Just give a thought about it. So yes, it should be bigger. So you are right if you are thinking that it should be bigger, because dilated time is the longer time than proper time. And what is the proper time in the question? Delta T naught, which is 8 years. So the dilated time should comes out to be greater than 8 years. So this gives us a way to check whether our answer makes sense or not, right? So now let's organize the information. So let's go on to the information page. Yes. So first I'm going to write the given and what we need to find. Delta T naught is given to us, which is 8.0 years. And the speed of the moving object is 60% of c. So which we can write as 60 over 100 times c, which would be 60 over 100 is zero point 0.6 times c. Now, C is already a known value, 3 times 10 raised to the power 8 meter per second. Now, what we are required to find? Delta T, as we have seen, dilated time. Again, whenever we are going to solve questions like this, we have to ask the questions. First, who is moving or what is moving? Second, which clock travels with the spaceship? Then, who is observing the spaceship? right? So after you answer all these questions, you can organize the information as we have organized, right? So let's check the concept very clearly. First, I'm going to write who is moving or what is moving in this case. This is the first question that we need to ask. Second, which clock travels with the spaceship or with the moving object? Which clock is traveling with the moving object? And the third question is that we need to ask, who is observing the spaceship? So to write the answers, who is observing the spaceship? Of course, somebody or the twin on the Earth. Second, which clock is traveling with the moving object? It was the spaceship clock. And who and what is moving? It was the spaceship. And whatsoever is moving, we know would be giving us the proper time. And that proper time is given to us, which is 8 years in the question. And of course, the time that we are going to measure on from the Earth would be the dilated time. And we know that dilated time should be greater than the proper time. So dilated time should be greater than proper time. So our expected answer should be greater than, expected time should be greater than 8 years, right? So let's write down the formula that we are going to use, which would be delta t equals delta t naught over 1 minus v square by c square. Now we can substitute the values. So delta t, we need to find delta t naught, it's 8.0. 1 minus v, I can write as 0.6 c square, and it would be over c square. So now I'm simplifying here. So delta t would be 8 over 1 minus, I can write 0.6 is 0.36. 0.6 square is 0.36 c square over c square. Now you can see c square and c square can be cancelled. As I told you, this is going to make our calculation work easy. So it would be 8 over 1 minus 0.36. Now if I'm going to solve this, I will get, you can also solve this using the calculator. So we will get around 10 years. So on solving this, we would get 10 years. So now let's compare the ages. So the twin that is observing the time from the Earth would be measuring 10 years. So more time passed on Earth. That means the twin on the Earth is older. By how much? It would be 10 minus 8, that is 2 years. And this matches our prediction because Earth should measure a longer time than the spaceship clock. So age difference is going to be 2 years. So the answer to the part A would be twin on the Earth will be older. And let's just write. So comparing the ages, as we have seen, 10 years is greater than 8 years. So for the final answer, we know that twin on the Earth would be older. By how much years? 2 years. The answer to part A is twin on the Earth will be older. For part B, the reason is that spaceship is moving close to the speed of light. So the moving spaceship clock runs slower compared with the Earth's clock. So therefore only 8 years pass for the astronaut while 10 years pass on the Earth. So twin on the Earth is older and spaceship is moving too close to sea. That's why there would be time difference. Now, next, let's move on to the question 2, which is muon lifetime. The question says a muon moves at 0.95 c relative to observer on Earth. Its proper lifetime is 2 times 10 raised to the power negative 6 seconds. What will happen to the lifetime as seen by the Earth observer? We have to justify our answer using calculations. So again, In this question, uh, uh, the most important phrase in this question is the proper lifetime. That tells us directly that given lifetime is delta t naught. So proper time is 2 times 10 raised to the power negative 6 seconds. Again, the next question that we should ask is who observes the moving muon? So Earth does. So Earth measures the dilated time. So before calculating again, should Earth see the muon lifetime as shorter or longer? So yes, it should be longer because Earth is measuring the dilated time. So again, we can write proper lifetime is given in this question and we need to determine the dilated time. So let's organize the information. Again, given is the delta T naught, which is the proper time. So let's write down the proper time, which is 2 times 10 raised to the power negative 6. So 2 times 10 raised to the power negative 6 seconds. V is, or the speed of the moving object is also given, which is 0.95 c. And now we have to find the delta t, which is dilated time. Same formula as we have used earlier, delta t equals delta t naught over 1 minus v square by c square. I will substitute the values. So delta t equals delta t naught, which is 2 times 10 raised to the power negative 6 over 1 minus v square would be now 0.95 c square over c square. Now you can take the square of, you can write down the square of 0.95, which will give us 0.9025. 0.9025 c square over c square. Again, c square will be cancelled. We will get 2 times 10 raised to the power negative 6 over 1 minus 0.9025. And on solving this, we will get 6.4 times 10 raised to the power negative 6. So 6.4 times 10 raised to the power negative 6 seconds. What is the interpretation? So the Earth observer measures the muon lifetime as approximately 6.4 times 10 raised to the power negative 6 seconds. So the proper lifetime was only 2 times 10 raised to the power negative 6 seconds. So from Earth's frame, the muon appears to live longer. This is very important result because muons are created high in the Earth's atmosphere. Without time dilation, many muons would decay before reaching the Earth's surface. But because Earth observes their lifetime as longer, more muons are able to reach the surface. That shows us that time dilation is not just an idea from science fiction movies, it is a real effect that can be measured. So proper time was 2 times 10 raised to the power negative 6 seconds, and you can clearly see the difference as the time would be observed from Earth would be 6.4 times 10 raised to the power negative 6 seconds. So lifetime appears longer to Earth observer. Muon appears to live longer because it moves close to c or speed of light. Right? So this happens because the muon is moving very close to the speed of the light, so its moving clock is observed to run slower from Earth's surface. So these are the things that we have to keep in mind. And let's see as the closing summary or common mistakes. Moving clock is going to measure proper time. Observer watching motion is going to measure dilated time or delta t. Dilated time is longer. At speeds close to c, effects it becomes important. Do not mix up delta t and delta t naught. Do not forget delta t naught is measured in moving objects frame. Using 0.60 or 0.95 whatsoever the speed of moving object is given instead of 0.6 c. So always mention that c. Saying both twins age the same, it's not going to be the answer. Not explaining the meaning of the result. So you should know the interpretation of the result as well.